Okay, good afternoon, everyone.
Afternoon.
I start with your questions. How did the review? First, we start with section 1.5, 1.7, linear independence and dependence. What questions do you have before I take on?
I have a question.
Yes.
About those that packet of problems that you gave alongside the
Yes.
homework, the chapter. Everything went well except for 1C. For some reason, the matrix isn't reducing for me. I don't know what's going on.
Okay, so we go through that. I mean, since today is a review for you guys, unless you want to introduce something new, which is I don't think so. So we go through this worksheet, and then I will, we'll have more review problems. So, but first, I want the definition to be clear in your mind, and then we proceed. So, suppose we have vectors in our N. So we say that they are linearly independent if what? Linearly independent if. What was the definition? What do we look for? If we try to solve the following equation, means if we try to find weight, x1 through xp, that make this combination the zero vector, if x1 has the unique solution or the only solution, it has one solution only, which is the zero solution. Means we solve this, we get one. Okay, and linearly dependent, make sure you know exactly the definition. Linearly dependent if this equation, the same equation, have a solution which is not all zeros. Have at least one non-zero solution. So this is the main definition, that one non-zero solution. So based on this, I will look at the worksheet I did give you, and after that, I will do some more problems with that. So I will take this worksheet. You guys should have it. All right. And we will do them quickly and see what your classmate had difficulties with. So my first question, we had those vectors, A1, A2, and A3. And my question, are they dependent or independent? In case they are dependent, I'm asking you to find a linear dependence relation among the vectors. And I reminded you what I mean. So first, let us see, are they dependent? So we need to solve, always, we have to solve this equation. And we ask ourselves, do we have a non-zero solution, or it's only the zero? Okay, so let us solve it. Now, if we solve this, it means we have the following system: x1 plus x2, 0, 0, x2, 0, and 1, 0, minus 1. And I insist on you writing the zero vector here. Otherwise, you don't know what you are doing. And this has three unknowns. So I'm looking for those weights. So we have to know exactly how many unknowns we deal with. All right, so we have to reduce. I try to give you simple ones to reduce. And 0, 1, 1, 0. That's a 0. That's a minus 1, that's a minus 1, and that's a 0. So, of course, reducing, you go to the echelon form, you don't stop anywhere before it. So one more step will give me 1, 1, 0, 0, 1, 1. And then I have to add, it's a 0, it's a 0, and this is 0. So these are my leading. All right, now right at this stage, are those vectors dependent or independent? I want quick answers from your part. So basically, I'm solving. I'm asking myself, do I have, if I solve this, do I have only one solution, or I have infinitely many? absolutely dependent, because what happened here? X3 is free. Correct? What does this mean? It means that every time X3 is free, it means that this equation has not one, not two, has infinitely many solutions. Has infinitely many. In particular, a non-zero solution. Non-zero means dependent. Okay, the question of dependence is being resolved. But question number 2 is, in case they are dependent, I want you to find a relation, a linear relation among the vectors. To do that, what we should do is the following. To find the linear relation, I need to find a solution of a non-zero solution. So to find the linear dependence, we need to find a non-zero solution, and I plug it back into the equation. Not all of them. I don't really care about all of them. That's not the point in this particular type of problem. The point is that find one of them. So to do that, we need to solve. So let us solve them. X3 is free. X2 is minus X3. X1 is minus X2, because that's how we read this. X2 plus X3 is 0. It means X2 minus X3, and X1 is minus X2. So immediately I need a non-zero solution. And then you can pick anything you want. I can pick X3 1 and X1 minus 1. But what does this mean to us? What's the linear dependence? It means that I'm solving for those scalars. It means if I take minus A1 minus A2 plus A3 is equal to 0. That's the linear dependence relation. I mean, there is something that the vectors are linearly dependent from each other. And if I have this, now I can express one of them as a linear combination of the other. So okay. Right. So this is going to give me what? It's going to give me that A3 is actually X1 has to be plus 1 because it's minus X2. So it's going to give me A3 equal minus A1 plus A2. So I expressed one as a linear combination. Yes. So I go back and ask myself, am I right? Is A3 minus A1 plus A2? Yes. Minus plus, that's a 0. Minus plus, that's a 1. Minus 1 plus 0, it's minus 1. And I'm definitely on the right track. So that's what dependence, it means that one of them could be obtained as a combination of the other. Independent, there is no question asked. All right, so that's really the idea of dependence. Now, the second one, let's look at that. Okay, are those dependent or independent? Without any question asked, what will be your answer?
Dependent.
We will do the math, but we want without dependent, because who can give me one reason why those are dependent? And we will do all the math required, but first I want to be able to interact with that. X3 will be free, all right? So let's follow. Not necessarily X3, one of them will be free. One of them. Not necessarily X3, maybe X3, I don't know. But at least one of them will be free, because we have 3 vectors in R2. So now the minute I try to solve those, so I'm going to solve that. Okay, any 3 vectors in R3, any 3 vectors in R2 will be dependent. And now let us see here the picture, and then I'll talk about the geometry of it a little bit. So very quickly, I will not dwell a lot on the echelon form. I should have a 0 in here. minus 2 plus 1, that's a minus 2, minus 2 plus 4, that's going to give me minus 4 plus 4, that's give me a 0 and a 0. Of course, I don't have to go to the reduced. I don't really need that. X3 is free. So we have infinitely many solutions. In particular, a non-zero. That's the one I want. Since I have a lot, in particular, a non-zero. So the vectors are linearly dependent. Linearly dependent, okay? So fine, absolutely dependent. I answered this question. Now I want a relation between the vector in case you're asked for it. If you're not, you're not. So to find a linear dependence, I need to solve. X3 is free, I'm done. Okay, how do I read this? Minus x2 equal to 0. Minus x2 equal to 0, x2 is 0. How do I read the first one? This one, we read it x1 plus 2x2 plus 2x3 equal to 0. But x2 is 0, this will leave me with x1 is minus 2x3, right? Now, that's not the relation. The relation is among the vector. It means you find a particular solution and you a non-zero particular solution and plug them back here. So I can take x3 to be 1, x2 to be 0. It has to be. I don't have choice for x2. This is minus 2. And now that's the relation between the vector. Minus 2 times a1 plus a3 is equal to 0. So a3 is 2a1. All right, are we correct? If we had paid a little bit attention, we could have noticed that a3 is twice a1, 2 times 2. So they are, again, another reason why they happen to be linearly dependent in this particular scenario. Okay, but in general, as we said last time, any 3 vectors in R2 will be dependent because 3 vectors, so we have 3 unknowns, but they are in R2, each one of them has 2 components. So they create a system of 2 equations with 3 unknowns. Therefore, we have to have a free variable, and because we don't have an issue with consistency, because we know we have at least a 0 solution, hence, because they're going to be dependent. Okay. Right, so this is just a quick review. Now, before I proceed to the other 2, the one of them, one of your classmates had difficulties with, geometrically, why any 3 vectors in R2, and it's crucial, R2 are linearly dependent. But if I have any 2 vectors, whether they are or they are not scalar multiple, it's irrelevant. Any vector here, any third vectors, if those 2 are linearly independent, it means they are not scalar multiple. You should always remember the picture of the 2 rows. And the question is, if this is my any vector, my A3, can I write A3 as a combination of A1, A2 in this particular picture that you see? And I tell you yes, because to get to A3, you go a little bit in the -1 and then a little bit in the direction of A2. So that's absolutely a linear combination. Regardless what A3 is, it's a linear combination. So any 3 vectors in R2 are linearly dependent. If 2 are scalar multiple, like the previous problem, they are linearly dependent. If they are not scalar multiple, 3 of them will be linearly dependent because of the geometry. I can always write A3 as a combination of A1 and A2. Now, I forgot which one your classmate had difficulties with, whether it was C or D, but whatever, we'll do both of them. So here I have 3 vectors. And those are 3 vectors in R4. So 3 vectors in R4 because they have 1, 2, 3, 4 components. That's about it. R4 is, it was C, very good. Okay, R4, it means we have 4 components. And are they independent or dependent? I have no idea. Absolutely no. That's too messy. So what we have to do is we need to solve. What do we have to solve? x1a1 plus x2a2 plus x3a3 equal to 0. Okay, that's what we have to solve. Now, question number 1. How many unknown do we have here? You have to be very careful with the number of unknown. 1, 2, 3 unknowns. So we have 3 unknown in this problem. Okay, now we need to solve it. So when I plug in the value of the vector here, we're going to generate a system. And the system will have for augmented matrix 0, 2, minus 1, 1, minus 3, 1, 4, minus 4, 9, minus 7, minus 5, minus 2 equals 0. And I insist that you put the zeros. Otherwise, you will be totally confused. So to solve for dot 3, I need to solve the system having this as an augmented matrix. Now, how do we solve a system? I mean, the way we always solve system, no more, no less. Okay. So if I'm doing this by hand, the first step is I need to create a leading right here. To create a leading right here, I cannot keep it a 0. I have to switch. And this is my favorite one because it has a 1 already in it. So make the switching easy. And then, and those I don't care how we write them. And a 0 and a minus 1, that's a 4, that's a minus 5 and a 0. So this is my leading. And now I need to make everything below my leading into a 0s. So definitely I need another piece of paper here. Okay, so everything below it into a 0. So I'm gonna need 2 operations. So 1, minus 4, minus 2, 0. This is safe, it's been guaranteed. And here, I have to multiply by minus 2 and add, give me a 0. Minus 2 is gonna give me a 9. Please help me if I do any mistakes because we'll mess it up a little bit. And minus 2 here, gonna give me a 4, minus 7, that's a minus 3 and a 0. Then I have to add. I have to add and give me minus 7 and a 0. Right, so this is a 1 and there is a leading here. Okay, so you can go different route. You can divide by minus 3 and switch, or okay, if you don't do that, what else can we do? If I use this as a leading, I have to make everything below it into a 0. So zero, that's safe. How can I make this into a 0? So I have to basically divide by 3 and add to R4. Right? 9 divided by 3, that's a 3. Minus 3, it's a 0. Minus 3 divided by 3, it's a minus 1. Minus 1 plus 8. Sorry, minus 1 plus 9, that's an 8. All right? And this. Now, I stop till I am in an echelon 4. Am I in an echelon 4? Yes or not? Am I in an echelon 4? Back to you guys. You don't stop till you're in echelon 4. No, it has to be a 0 below it. No way out. So once I am in echelon form, I stop. Some of you are stopping before and you'll get into definitely problems. 0, 9, minus 3, 0, 0, 0, minus 7, 0. And it's easy to get a 0. So I will take the third row, one possibility. I mean, there are 2 ways. Either you divide by 7, you make this into 1, and then you do another operation, or because we just multiplied by 8 over 7, plus R4 into R4. That's one possibility. So multiply by 8 over 7 times minus 7, give me -8 plus 8, it's a 0. Now these are my leading here. Okay, now back to you. Do I need to go to the reduced echelon form in this problem? Or it's a waste of time and you don't have that much during an exam? Do I need to go to the reduced echelon form, or I can solve and know exactly what's happening at this stage? Remember, my only goal now, for now, is do I have a non-zero solution, yes or not? That's really what I want. Okay. Question number 1. How many unknown do we have? I ask the same question again. How many unknown do we have? 3. It's not 4. Not because you have 4, it's 4. 3 unknowns. And let us solve them. How can we read this? -7x3 equal to 0. So one way you can solve it. This read -7x3 equal to 0. It means x3 is 0. Back up. Leading to 0, but x3 is 0. It means x2 is 0. You don't have to go to the reduced echelon form. It's too much waste of time. We don't need that. And the first one, of course, we have x1 minus 4, x2 minus 2, x3 equal to 0. But those are 0. It means x1 is equal to 0. So since x1 equal x3, sorry, equal x2 equal to 0, there is one solution, a unique solution. It means the vectors are linearly independent. So solution unique. That's really what we want. We want a unique solution. Solution unique. It means linearly independent. Okay. Now, one comment here is that you can solve, or if you want, you can say the following. Since 0, 0, 0 is already a solution because I'm solving a homogeneous system. It means if I plug in 0, 0 here, I will get 0. So I know that there is a solution. But since I have a leading in every column, except of course the last one, it means every variable is basic. There are no free variables. Because there are no free variables, the solution is unique. But it is unique and it has to be 0 because 0 is already a solution. Since you have one of them, then it has to be the 0 solution. So another way to say this, since every variable is a basic in this problem, it means the solution is unique. And since 0, 0, 0 is a solution, it means that's the only solution. And that will show the linear independence. Okay. Questions for those? Right. So we finalize this by having a look at the last one, and we will look at it very quickly, and then we proceed. Okay, so here again, I have 4 vectors in R3. And the question, are they dependent or independent? And if dependent, find the relation between them. So what do you expect here? Dependent or independent? But dependent. Okay, so because, and I need to find the dependence relation. So here, I need to solve x1a1 plus x2a2. I have to solve this. Equal to 0, okay? And this is gonna generate a system. How many unknown? 1, 2, 3, 4 unknown. How many equations? It depends on the number of entries. So when I'm gonna solve, it's gonna generate a system of 3 equations with 4 unknown. So one of the unknown cannot be a basic variable because the maximum number of basics has to be 3. Since I have 3 rows and every row can contain 1 leading, so the maximum number of leading is 3. It means the maximum number of basic variable 3. It means we have to have a free variable making them dependent. But now I want a little bit more. I want the linear dependence. So the only way to do that, we have to solve this. All right, so we solve it. I did solve it, I think. I got something like that. You guys should check this out. 1. I got this as you realize in this particular problem, I'm not going to the reduced echelon form because I don't want to do more work than I have. So now this is leading, this is leading, this is leading. Those are basic. So Act3 is free. Okay, so what does it mean Act3 is free? It means we have infinitely many solutions, hence a non-zero solution. Not zero. Okay, so dependent, absolutely. Okay. So now find the linear dependence relation. It means if they are dependent, it means I should be able somehow to express one as a combination. Which one I don't know, but let us see how we can do it. And the goal of this exercise is really to make you understand what dependent means. So let's find a non-zero solution. Okay. To do that, we have to solve, and we'll do it as quickly as possible. We need X3 is free. Sorry, my apology. X4 is free. And I read this. This read X3 minus X4. It means X3 is X4. I don't have to do a lot because I need one. So I don't really have to solve fully. The first one tells me that X2 is X3 minus X4. And the first one tells me X1 is minus 4X2 plus 3X3. I want one. I want one. So I'm not writing it in parametric vector form. I'm not doing anything. I'm just going after one solution. So I pick X4 to be 1. X3 is 1. X2 is 0. And X1 is 3. What does this mean? What does this mean? It means if I plug them back here, it means 3A1, 0A2 plus A3 plus A4 is equal to 0. Dependence allow me to find this relation. If they are independent, that is, I cannot find those weight. Only 0 will do. So now I can express one. So I can write, for example, any one you want. So A4 will be minus 3A1 minus A3. So I can go back and check my work. Am I right? So if I take minus 3A1 minus this, do I get that? Let's see. So this is 0. I take minus 3 minus, minus 3 minus minus 3, that's a 0. I multiply this by minus 3, I get a 6. And I get a 6 minus 5, which is a 1. I multiply this by minus 3, giving me a 12. And a 12 minus 7, which is 5. I'm absolutely on the right track. All right, so that's really dependence and independence. Okay. Let us take care of this worksheet. Do you guys have any questions or yourself before I proceed? Right. Okay, let me, an important remark, nothing new. It's actually everything is remark. Sometimes we have a matrix A, and let us say this matrix have columns, of course. So let us say this matrix is, I'm gonna pick up one of the problems we did as entries. So for example, this matrix is 0, 2, minus 1, 1, minus 3, let us say 1, 4, minus 4. And this is my matrix based on problem part C here. Okay. Right. And the question is, what does it mean? Show that the columns of A are linearly independent. Or dependent, what does it mean? But let me emphasize independent. Suppose I tell you, show that the columns of A are linearly independent. Basically, this is really equivalent to show what? This is X1, sorry, this is my A1. That's really what it means. A2, A3, that's what it means. It means is to show that the vectors A1, A2, A3 are linearly independent, right? And this means that to show the following, x1a1 plus x2a2 plus x3a3 equal to 0 has only the zero solution. So far, I'm just regurgitating what we said. But this is really, I'm going to now introduce matrix times a vector. So this is equivalent to show that the following equation. What should go here? It means if this is A1, so basically that's A1, it means the matrix A, minus 3, 1, 4, minus 4, 9, minus 7, minus 5, minus 2, x1, x2, x3 equal to 0 has only the trivial solution. So it's basically like showing that the homogeneous system, Ax equal to 0, has only the trivial solution. Okay, so this is just a connection showing that the column of A are linearly independent is basically showing that the system Ax equal to 0 has only the trivial solution. And sometimes people write it in this format. I want you basically to be absolutely familiar with it, right? With this in mind, I would like to discuss some of the problems that I assigned from section 1.7, and then I will go to the exam review, the one I gave you, unless you have specific questions yourself. Okay. So one of the questions in the book, for example, is the following. Suppose A, so that's number 23 in the book. A is 3 by 3. Okay, and the columns of A are linearly independent. So this is what I know. And the question is possible echelon form of A. Okay, so A is a 3 by 3 matrix. So already you should have a picture in your mind. So we have bing, 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 bunch of stuff. The columns of A, so now these are the columns, are linearly independent. So if I call them A1, I call them A2, I call them A3, those are linearly independent. Independent. Okay, I want you to describe the echelon form of A. How should A look like? If they are linearly independent, what should we expect here? May I take A and reduce it? Because that's a 0, because it's a 0, even reducing it will get me a 0. But what should be happen here? What should we expect? It should have a leading in each column. Absolutely, I need a basic. So here, I don't care, a leading, actually a leading, doesn't have to be 1, it's just a leading. Anything, this has to be leading. So when I take it, I reduce it, I should have this type of picture. That's the picture fully of linear independent. 3 pivot, any format you guys want to tell me. So let's look at another one. Let's meet 27. Okay, suppose we have 7 by 5 matrix. 7 by 5 matrix. And the columns are linearly, no, sorry, I read the question clearly. How many pivot columns must a 7 by 5 matrix have if the columns are linearly independent? So we have 7 by 5 matrix. if the columns are linearly independent. Columns linearly independent. And the question is, how many pivot are we going to have? Or how many leading? I prefer leading. It's easier for you. Quickly. 7 by 5. How many leading? Okay, 7 by 5. The maximum number I need a leading in each one of the columns. That's the only way I can guarantee linear independence. I have to have 5 leading. So that's really the picture that you should have. All right. So these are some of the questions for linear independence. Now I go back and did you guys go through the review that I gave you, which is my old exam, as you guys know? Did you go through it? Anybody? All right, so I will discuss the problems that I know that students usually have difficulties with. Page number 1 from the old exam, none of you, usually students don't have difficulties with. You guys have to review carefully what I mean by parametric vector form, because you will be asked these questions. And once you know how to write it parametrically, you are in a safe territory. Right. The question that, there are 2 pages that I would like to cover with. The question that you guys had difficulties with prior, and you still have difficulties, is when you discuss solutions. So I will do one of them, I leave you the other one, I leave it for you. So suppose I have this system, and my question is, there is a variable A hanging in there. And for some A, we have solution, for some we don't. And my question is usually, which parameter will allow a solution, infinitely many solutions? Always the way we do those is by starting by reducing. And usually I give you matrices where the reduction is not hard. So you will not get into problems with that. So we're gonna start the reduction process. So this is equivalent to, that's my leading here. It's a 1, it's a 1. It's a 0, it's a 1. And that's a 0. Minus 2 plus 3, it's a 1. Minus 6. And then minus 2. Sorry, I lost my chain of thought. Minus 6, which is going to give me a minus 4. Okay, so definitely we're not in echelon form. We stop only at the echelon form and then we proceed. So this will require one more operation. And be careful with the operation. If you do an algebra mistake, you will have a nightmare in the making. 0 minus 1 plus 1 is a 0. Minus a will give me a square minus a minus 6. And then here I have to multiply by minus 1. Minus minus, that's a plus. And this would leave me with a minus 3. So that's my echelon form. And I said no reduced echelon form, just stop at the echelon form. Okay, now the question is, for which A's does the system have infinitely many solutions? Right. When do we have infinitely many? Infinitely many occur under 2 conditions. We need a free variable. But is this enough to have infinitely many? Does a free variable enough to have infinitely many? Back to you. That could be a true or false statement. I can ask you if a system has a column without a leading, does it mean the system has infinitely many? What should be your answer? Yes? Anybody can argue with Chris? So, if I give you any system, the minute there is a free variable, the minute there is a column which is has no basic. Suppose I have 1 here, I have 1 here, 0, 0, bunch of stuff, that's a 0, bunch of stuff, and bunch of stuff. Okay, so this is, does this have to have infinitely many? What can be the issue? What can the issue be? Does this guarantee infinitely many solution? Right, we have to make sure we have consistency at the end. So if I had a leading here, even though we have a free variable, but big deal, we don't even have solution. So the free variable doesn't really make sense. So for us to be able to solve, we have to make sure that if we have a free variable in a way, it means we have a column to the left of the last one that doesn't have a leading, and we have to guarantee the consistency of the system. That's how we can guarantee the consistency. So we need those conditions to guarantee that. So for this to occur, I definitely want a free variable here. So it means I want this to be 0, but this is to guarantee the free variable only. Now I want the consistency, and to guarantee the consistency, I don't want them equal to each other. That's not what I am after. I want the free variable and this one to guarantee the consistency. That's really, and this is for the consistency. That's really how we reason through that. So now we find, how can this guarantee? So, okay, this is equal to 0. I factor this out. That's give me a 2, and that's give me in, let's see, this is a minus a 3, because there is a minus a here, and this is the a plus 2. So this will guarantee a equal minus 2, a equal to 3. And for this to occur, I need a equal to 3. But now I need both of them to be satisfied, not only one. If one is satisfied, it doesn't work. So for both to be satisfied, a has to be equal to 3. So this would be the solution. A has to be 3. All right, that's the consistency. All right, I'm not going to do 5. I'm going to keep working with the same problem. And I'm going to add the question. When the solution unique? Means one of them. For which value of A, solution is unique. Okay, I want you to reason through that, not to, whatever, just reason. Don't just throw a statement. What guarantee a unique? We're working a lot with uniqueness. What always guarantee the uniqueness? I'm listening and reading. The only thing I don't do is see your faces. Every column has a leading. This is absolutely correct. What guarantees every column has a leading? This one has a leading. It means in terms of my situation, X is basic. No question asked. Y is basic because I have a leading. So it's only Z that may or may not be a basic. But if I want a unique, I want Z to be basic. It means I need A squared minus A minus X to be non-zero. That's the only thing I need. A lot of you are, I don't know what they do, but you put this equal to that. This is absolutely nonsense. I don't want those to be equal. I don't care. I mean, if my system looked like this, 2, 0, 0, 2, 3, that's a consistent system because I can read it as 2z equal 3. I can solve for z. It's not that I don't want them to be equal. I want to guarantee a basic here. That's what I really want to guarantee. So I need this one to be different from 0. And if this is different from 0, I'm sure the system is consistent because if this is non-zero, I can immediately solve for z. There is no consistency issue in this case. So now the problem will be solved. This different from 0, and then I already factored it out. Means I need A different from -2 and A different from 3. Okay, so that's really the uniqueness criteria. The inconsistency criteria is, I think the inconsistency is an easy situation. The inconsistency, it means I cannot have a row of the form 0, 0, non-zero. It means the inconsistency occurs when the last column has a pivot. So in this case, when the inconsistency occurs, for the inconsistency to occur, I should have the following scenario. I cannot have a pivot in here. So for this to occur, if this term is 0 and this term is non-zero, that's really what creates the inconsistency. So if I have 0, 0, 0 and a non-zero term, that's inconsistency. And this will occur, so I need both. The first one occurs for a equal to 3 and a equal -2, and this will give me, I need a different from 3. So for both occur when a is -2. And that will give me the inconsistency ideas. All right? Very good. Okay, the second one, number 5, I think by now you should be able really to do it yourself. I will not do it. Sorry. This one is verbatim what I did a minute ago about dependence. You guys should be comfortable with that. Problem number 7, I will definitely look at it, and the true and false questions. So number 7 is I gave you a bunch of vectors. And the first question is complete the following sentence. The vector B in the span if. And your answer should express the meaning, not the algorithm. So what do I mean by that? I mean that I really want you to know what does it mean to be in the span. In the span mean, remember the span is all linear combination. All, make sure you review the definition. All linear combination of A1, A2, and A3. So be in the span if. We can find weight. That's what it means. You can find weight. You can call them what you want, x1, x2, x3, such that B is a combination of them. That's what a linear combination, what a span is. It means I can write it as a linear combination of those vectors. And that's what I'm expecting in the scenario. Okay, that's what the span, every possible linear combination. Now my first question is, under what condition on B1, B2, B3 is the vector in the span? So the vector is in the span, it's basically I can find a solution. So we need to solve and see under what condition we have. So we have to solve x1 times this plus x2 times that plus x3 equal. Always write what you're trying to do. And this way you learn, equal to b. So this is 1, 0, 1, 2, 3, 3, 0, 3, 1, b1, b2, b3. So basically I give you 3 vectors. And my question to you, okay, we have 3 vectors in R3. And I picked one, arbitrarily one, and tell you, okay, is this vector in the span regardless which vector I pick? So does this always occur? So we have to solve the system and ask ourselves, do we have a solution regardless? So we always solve B1, B2, and B3. Okay, we solve. And I try usually to give you a system that's not hard to solve, to make it a little bit easy for us. So we solve, and you guys do it. And of course, 1 minus 1. So you do the work and you stop when you reach the echelon form, and I will pick up the answer I got. So we don't have to go through that. So I'll get this one. And this is B1, and I got 1/3 B2, and this is gonna give me minus B1 plus B3 minus 1/3 B2. So you guys do the work and you get that. And now the discussion and what it means. So now my question is, under what conditions is the vector B in the span? So this vector, so what's the relationship that should exist between the entries of the vector B to guarantee it is in the span? So the vector B will be in the span as long as this is what? So B in the span is system is consistent. What does it mean consistent? It means for this to be consistent, what should be the condition on that? What should be the condition? It means which numbers I can plug in here to guarantee that this vector is a linear combination. So what relation should exist between the entries? Finish my sentence.
The entries all equal 0?
It has to be equal to 0. So that's the relation between. So it means not every vector can be written as a combination of the 3 vectors. Not every vector, not everything I throw at you will do. The vector should satisfy this condition. Okay. Now, my last question here, is the span equal R3? What does this mean? It means if I pick any vector in R3, can I write it as a linear combination of the vector A1, A2, and A3? So now I have the 3 vectors in R3. I don't know how they are in a way. And my question is it R3? Let me repeat what it means. It means if I take anything in R3, anything, any vector, that's why I gave you any vector. Can I write it as a combination? That's what it means, it's in R3. Can anything be written as a combination? Now, of course, I prepared you before. If so, explain why. If not, give a specific vector B, which is not in the span. So the question is that, okay, you have 3 vectors in R3. Can I write anything as a combination? So what will be the answer? Is everything in the span? According to the previous one, so basically I'm asking you, can you solve this regardless what B1 and B2 and B3 according to this? And the answer is absolutely no. And explain why. Because, why not? Because if I take the following vector, which vector? I take the following vector, B is not in the span. And which vector and why? Okay. Which vector shall I take? I want an entries for a vector. B tells me that which one are in the span, they are those that satisfy this condition. Means if I take a vector where the entries do not satisfy this condition, it means when I try to find the weight, I get inconsistency. So if I want a vector that this is not the case, it's enough for me to pick a vector that doesn't satisfy this condition. So if vector doesn't satisfy its condition, I don't know, you will pick anything. Suppose I take B1 to B1, and I pick I don't know, I pick B2 to B1. What shall I pick P3 so that this condition is not satisfied? What shall I pick this one? Not to satisfy this condition. If this is -1 and it's -1/3, I can pick B3 anything. I can pick it to B3. If I do that, then -B1 plus B2 -1/3, sorry, B3, B2 is definitely not 0. What does this mean? What does this mean to you? It means if you try to solve this augmented matrix, you put A1 here, A2 here, A3 here, you try to ask yourself, can I find those weights? You're gonna come to an inconsistent system. It means the vector B is not in the span. So is the span equal R3? It's very mean that can I write anything? If you throw any vector at me, Can I write it as a combination? And my answer, no, for those particular vectors. For other vectors, yes, I can, but not for those particular vectors, right? Okay, let's do the last page, unless you guys have questions. You don't. So true or false? And I may ask true or false and justify. It doesn't have to be always true and false. Okay, A, the span equal R2. Let's see what does it mean. It means, can I write anything in R2 as a combination of those two vectors? Yes or no, justify. Who say yes? Who say no? And comment. Means, can any vector in R2 be obtained as a combination of those three vectors? What can you say just by looking at them, not at the solution that you guys have? Yes, because. Yes, because. If you say yes, we have to justify. It means if I take any vector, can I write as a combination? We can do this algebraically. We can do it geometrically. And I will do this one algebraically. Now, three vectors in R2, but how are those three vectors? Now let us think a little bit. This vector is 1, 2. This vector is 0, it doesn't contribute anything. And this vector is 3, 6. Watch carefully how this vector is. If I'm going to draw this vector from here to here, we have to make sure that they are not scalar multiple. Multiplying by 3, multiplying by 3. So if I take this vector 3, 6, it's going to be that much. So now I'm taking the span of those two vectors. It means I'm taking every possible linear combination of them. Anytime you scale those vectors and you add them, you are on this line. So there is no way you can get this vector from them. So that's geometrically no, so false. Because if you just look at them geometrically, because the vector 3, 6, the 0 doesn't really play any role, is 3 times the vector 1, 2. So the span here, this is nothing more than a line through the origin in the direction of the vector 1, 2. Okay, so even there are three vectors in R2, but not any three vectors in R2, we have to be very careful. In this case, even though there are three vectors, one is the 0 vector, so it doesn't really do anything, and the other two are scalar multiple, forget it. We cannot get all of R2 from there. So be very critical of what you have. Okay, B. Is R2 equal the span of 1, 2, and 2, 1? Means, can I get every vector in R2 from those? Geometrically. So let us see. 1, 2, and 2, 1. Are they scalar multiple? Here. From 1 to 2, you multiply by a 2. From 2 to 1, no. So those vectors, the minute I'm going to draw them, 1, 2, that's one of them. The other one is 2, 1. That's the other one. Okay, so now the idea, is it equal to R2? It means if I pick any vector in R2, can I write them as a linear combination? And really the answer is yes, because I can reach geometrically, and in a minute I'll do that algebraically. Anything could be obtained this way. So that will be a yes. Algebraically, how do you do it? Algebraically, you're going to ask yourself, if I take any vector, B1, B2, any vector, can I find weight such that, can I always find weight so that I can reach the vector B1, B2? In other words, can I find a solution regardless of what B1 and B2 is? Okay, let's do that. So let's do this carefully. So I'm asking myself, can I always solve regardless what my vectors are? So I put 1, 2 here and 2, 1. can I always find the weight to reach this vector? Okay, we always do what we always do. We basically start thinking 1, 2, B1. Minus 2 plus 2 is 0. Minus 4 plus 1, minus 3. And here, minus 2B1 plus B2. Another question to you. Do we always have solution regardless of what B1 and B2 is? Or there are vectors where we have inconsistency? What can you say? Let me rephrase this question. Suppose instead of B1 and B2, I take the vector 5, 6. And my question, can I write 5, 6 as a combination? What will be your answer? You solve. You're going to get a 0 here. You're going to get a minus 3 here. Minus 10 plus 6, minus 4. Can I write 5, 6 as a combination of this vector and this vector? Yes, because I can solve for it. So if I'm finding the weight, I can solve. So 1 will be minus 4/3 for the first weight. And then I solve for the second weight. I can solve because I don't have inconsistency. Now, if instead of 5, 6, I put the vector pi and e, your favorite numbers, can I write pi e as a combination? Do we have any issue with the consistency? Again, the same operation, 0, minus 3. This one is pi, and this would be minus 2 pi plus e. Can I find the weight? Yes, because I can solve, so I can find the weight. So what I am trying to tell you here, no matter what B1, B2 is, we have consistency here. It means if I try to find the weight, that's really what starting point. So if I take any vector, if I try to take x1, x2, this tells me, yes, you can find a solution because this is consistent, always consistent. Why is always consistent? Because there is no way we can get a 0, 0, and a non-zero number. This cannot occur. Why it cannot occur? Because I have a leading in every row of the coefficient matrix. I have a leading here, I have a leading here. This scenario cannot stop, cannot occur. So hence, no matter what I plop here, I can always find a solution to that. So the span has to be R2 because everything will work. All right, C. This is harder. Is the span equal R3? Again, since there are 3 vectors, we actually don't know. I ask myself the same question. So if I take any vector, B1, B2, B3, can I write it? Yes or no? That's really always the same question. Also, I don't know. I have take it and reduce it and ask myself, are there some values of B that get in the way? If yes, it means we don't get every vector in R3. If at the end I get a bunch of leading, then the answer is yes. So the answer is whether I can reach a consistency or I cannot reach a consistency. Now D. If A1, A2, A3 are linearly dependent, then A3 must be a linear combination of A1 and A2. True, false, justified. Somebody said false because so those are dependent vectors. They are dependent. It means one of them is a linear combination at least. Then A3, I'm telling you, must be a linear combination. True or false? I think I gave this as a homework. All right. Somebody tells me false, we have to justify. What do I mean by justify? It means give me an example of three vectors, A1, A2, and A3. I want A1, I want A2, I want A3. I want them linearly dependent, but I want A3, not a combination of those two. There is no way you can get to A3 by combining A1 and A2. Who can think of easy examples? Anybody can think of any example, they can unmute and tell me the example. If A3 is a scalar multiple of A1 or A2. So suppose I take A1 to be 1, 0, 0. What do you want me to take A2 and A3? So I can take A2 to be 0, 0, 0, 0. So A2 is already a scalar multiple. And then I can take A3 to be 1, 1, 0. And now, question addressed to you. Can A3 be a combination of A1 and A2? Can A3 be written as, is it any way? Is there any way I can combine those to get A3? Any way under the sun? And why? Immediately the answer no. Because if I combine those two vectors, the second component, regardless what I put for weight, is going to be 0. So there is no way I can get A3. You can also set up your system. That's again, but there is no way, because any combination of those two should give me the 0 vector. So A3 cannot be obtained as a combination of those. But those vectors are linearly dependent because A2 is 2A1. Means my vectors are linearly dependent. Now, E, usually shouldn't get that no. Which ones I got? I don't know. If a linear system has more unknown than equations, so we have more unknown than we have equations. So let us think about, let's pick a picture. So 3 unknowns, let us say something in our head, and 2 equations. Just think about it. Then it must have infinitely many solutions. True or false? True. If it's true, if. Who want to finish my if? If what? If it's consistent. If consistent. It doesn't have to be consistent. So we have to be very careful to the wording. So the answer here, must have infinitely? No, it must not have. The answer is false. The answer as a whole, the answer is false. Okay, it's true only if we guarantee consistency. So if I phrase the question like this, if a consistent linear system has more unknown than equation, then the system must have infinitely many solutions, then true, no doubt about it. So we have just to be careful with the consistency. All right, F. For those questions, you have to imagine the scenario. If the system has more than one solution, so if you solve AX equal B, so you have this non-homogeneous, and you get more than one solution, will the homogeneous one have to have infinitely many? True or false? Think about it a little bit. If AX equal to B, so this is A and this is my B, it has more than one solution. So this is AB. Always try to imagine the scenario. It has more than one solution. So I don't know how many equations, I don't really care, but I should know what's happening here. So what do you think, true or false? True, true, absolutely, because If when I reduce this, it means one of the column, one of the variable is free. So one of those variables is free. So if I'm gonna go to A0, the only thing that changes is the last term, and one of the variable would remain free. So we definitely have infinitely many solutions. Now the last question. If the system is consistent, and when the augmented is reduced, the last row is zeros, then the system should have infinitely many solutions. So the picture is that you have system, it's consistent. You reduce. And when you reduce, the last row is zeros. Does this guarantee infinitely many? If you say true or false, so I'm reading false, I need reason. I want you to think about it because it's a common mistake with students. The minute I say a row of zeros, yeah, that's infinitely many. But it's not false because all column might have a leading, absolutely correct. So I have to have a really nice picture here. So if I put 0, 0 here, so I can have leading here, 0, 0, 0. I'm completing what I did. And then I can have a leading here, 0, 0. I can have a leading here. So as you realize, my matrix is growing now, so I can really fit out my scenario. That's the scenario. It's like having 1, 2, 3, 4, 5, like having 4 vectors. So that's a scenario of 4 vectors in R5. So the last row is a bunch of zeros, but we have, in every column, we have a leading. So it doesn't have to be infinitely many solutions. Okay, so if there are more rows than column, we have to have that scenario, but not it has to have. I mean, this should be satisfied for this to occur. Okay, so not every time we have a row of 0, oh, it's infinitely. No, it's not the rows of zeros that cause infinitely many solutions. What causes infinitely many solutions is a column without a leading. That's really where the infinitely many solution comes into the picture. Okay. So this is an idea of, the exam that you guys should expect. Please go over what I didn't cover and go over some of your homework. The only thing I didn't cover in this exam with you is you definitely have to the multiplication of a matrix times a vector. You should definitely understand both definition and crucial parametric vector form. I mean, I'm telling you ahead of time, you will have to do parametric vector form. So even if I didn't do it, you should be able to do that. Like number 5 has to do with matrix times a vector idea. So I gave you a bunch of vectors and I gave you W to be this. And my question was fairly simple. Write W as the product of a matrix and a vector. There is one goal behind those problems for me. The goal is that do you remember the definition of a matrix and a vector? So this is give me minus 2v1 plus v2 plus 3v3. That's my W. And as I said, I definitely understand this definition. So it's minus 2 times that plus this plus 3v3. So that's what I want you to understand. So this is 1, 0, 1. 16, 4, 1. So a matrix times a vector. A matrix times a vector. Now, let us remember, when we define the product of a matrix times a vector, our first definition is the linear combination of the columns of A, where the weight of the combination are this. So these are the weights, and the columns are that. So it's not very intuitive, but it's crucial. So that's a matrix. And that's my vector. You can call it anything you want. Right? Okay, so unless you guys have a question yourself, I finish my review. For the exam, I will put the exam, I will open it 10 minutes ahead of time. Is it all right with you? Or do you have classes? Who have objection to that? Any student have objection to that? Anybody else? No objection. Okay, so I'm gonna put it 10 minutes ahead of time. So our class time meet at 2 o'clock. So the exam will be out at 1:50. Now, it will be very nice if you guys can print it. So those 10 minutes give you enough time to print. If you can't, that's okay. I cannot, force you to have a printer by any stretch of the imagination. If you can, just print it. And I will appreciate one PDF document. I will appreciate one PDF document, not like 5 pictures. It's hard to grade with that. So if you guys know how to put the whole into one PDF document, it would be very much appreciated. And for those who don't, you need it anyway with those online teaching. You can download Adobe Scan on your phone. There is something called Adobe Scan. You can download it on your phone, and then you can just take pictures, and it will by itself turn it into a PDF document. So for those of you who are not familiar with, there are different formats, but Adobe Scan is one that you can put it on your iPhone or whatever phone you have. You snap pictures, and it will turn it into a PDF document, if you guys can do that. Okay. All right, I'm done. If anybody has a question, can stay with me. Good luck.
Professor,
Yes.
what was the answer to number 8C?
8C. Let me look at it. I don't know. I think they were, I don't know. I think they were independent. You have to do the math. I cannot just look at it and tell you.
No, it's from the old exam that we just went over. I missed it. It was the true false question.
8. Sorry. The answer should be false.
Okay.
Absolutely. Because my question must. No, it must not. It could be inconsistent.
I think you said C.
Oh, yeah,
C or
C,
E?
C.
Oh.
C. Sorry about that.
Okay, see, let me work it out. Because this is one of those questions that I cannot just look at those vectors and just, look at them. So if I work it out, it means I say, okay, can I write anything here and still be safe? So what I mean by work it out means I ask myself, if I plug in any vector here, can I write it as a combination? Are you with me?
Yeah.
Yeah. So I actually a little bit, I reduce quickly and ask myself, can I always do it? So usually I have to flip here, 1, 0, 1, V3, 1, 2, minus 1, 1, 0, 1, V2, sorry, B2, 1, 2, minus 1, it's a B3, 2, 3, minus 1, B1. Do you understand why I'm doing this?
Mm-hmm.
Do you guys understand why I'm doing that?
You're rearranging?
Yeah, why did I do that?
Oh, okay.
Why?
So you could put it in echelon form easily.
Yeah, but what do I want here?
A 1 is a leading?
Yes, because the math is easier. The math will be easier, okay? The math would be easier. So dealing with 1 is easier than dealing with a 2. Now I can go back. So minus 1 plus 1 is 0. That's a 2. Minus 1 minus 1, that's a minus 2. And then I will have here B3 minus B2, right? Stop me if you don't follow.
Okay, yeah, I see.
Okay, stop me, because I guess, if you don't, I told you several times, I don't see your faces, which is problematic. Minus 2 plus 2, it's a 0. That's a 3. Minus 2, that's a minus 3. And then minus 2B2 plus B1. Okay? And the question is that is it consistent? I cannot answer a question unless I get to my echelon form. Prior to that, I can't. So this is a 2, and this is a leading. Okay, I have to get to the echelon form. So what would you do if you were me? What would you do to get your echelon form? What would you do?
You could multiply row 2 by, what is it, 2/3?
No, it should be 3/2.
Oh, yeah, 3/2, sorry.
Or, because I don't like to do a lot of math. I divide by 2.
Okay.
Okay?
Mm-hmm.
Just to make it easy, right? Just to make it easy. And then I can do that here also, but now I don't want more fractions to deal with. And now I'm almost done. Well, I'm almost done. And this here, 0, minus 3 plus 3, it's a 0. Minus 3, that's a 3, it's a 0. What do you think? Do you think we can find a solution regardless what the value of those are?
Mm,
Are we going to have issues for some values?
yes.
Yes, absolutely.
It's
Why?
because x3, the third variable is free, right?
No.
No.
No. No. Not because the third variable is free.
Oh, because of the inconsistent
Exactly.
form and the
Exactly. Because I can have inconsistency right there.
right. So you can't. It's false because you can't. It's inconsistent.
Exactly. So it
Okay.
means there are vectors that there is no way I can write them as a combination.
Gotcha.
Does it make sense?
Yeah.
100%.
Mm-hmm.
Okay, that is not the free variable. That's not the issue here. The issue is, can I find a solution for everything? Can I find a solution regardless what I put for B1, B2, and B3?
Right.
And the answer, no, because some of them is going to give me an inconsistent situation.
Okay.
If
Okay,
it
it's not the
wasn't,
free, it's crucial, not the free variable. No, it's the consistency. In this particular problem, my issue is it consistent or not? It's not whether it's infinitely. I don't care about that aspect in this particular scenario.
Professor,
I'm listening.
given the situation, if it wasn't inconsistent and it was consistent, where would we go from there?
It means any vector could be written as a linear combination. It means
Okay.
the span is all of R3, absolutely equal to R3. Let me give you a scenario. Are you done with that?
Yeah.
Let me change the scenario. And that's easy. Suppose I take the following scenario, the following vectors. 1, 0, 1. And I'm gonna try not to make something hard. 1, 1, 2. And I'm gonna take a third vector. Okay, so that's my A1, that's my A2, and that's my A3. All right, I made up those vectors. And then I'm asking you, is the span but equal to R3? First, you have to understand what I am talking about. Crucial. So what does this mean? It means if I pick any vector here, any vector, regardless what I put here, can I write it as a combination of A1, A2, and A3? That's what I'm asking. Okay, so I don't know by looking at them, because it's very possible if my A1, A2, and A3 are in the same plane, that's really the geometry, and B is outside this plane, I cannot write it as a combination. So that's really the geometry. So how are those vectors with respect to each other? Since we cannot we cannot do that mentally, we have to do it algebraically. So the question now that if I take any vector, be any vector, is B a linear combination of A1, A2, and A3? Any vector. That's what it means to be in the span. It means, can I write anything here as a combination? But what does it mean? It means, what am I solving? I'm solving this system. 1, 1, 2, 2, and 4. Am I correct? Is this the system I'm solving? Yes or no?
Yes.
Now, how do we solve this system? We put in the argument. And what is my goal? Can I always find those scalar regardless what I put here? As I said, if I put pi e and square root of 2, can I write this as a combination? That's really what I'm asking. Anything. Can I actually find the weight? All right, I put now my matrix and try to ask myself, can I always do that? And instead of doing it for every vector, which is absolutely impossible, I do it for a generic vector, and then I ask myself, is it possible? So I'm gonna go to my augmented here. 1, 1, 2, B1, that's that. 0, 1, 1, B2, and then minus 1 plus 1, it's a 0. Minus 1 plus 2, it's a 1. Minus 2 plus 4, it's a 2. And this is gonna give me B3 minus B1. Am I correct? Yes or no?
Yes.
Okay, now I'm not done. Now I keep going. 1, 1, 2, B1. 0, 1, 1, B2. Okay, I have to make this into a 0. Minus 1 plus 1 is a 0. Minus 1 plus 2, it's a 1. And then I will have minus B2 plus B3 minus B1. Okay? So now I am in my echelon form. And now my question to you is the following. Can I find a solution? Is the system consistent regardless of the entries of my vector? Yes or no? Is the system consistent regardless of what I put in here?
If negative B2 plus B3 minus B1, if that was happen to be 0, would that change anything? Would that be significant?
Try to answer your question. Let us say it is a 0 here. What will be the solution? X3 will be what?
0.
Right. Is there a problem with that?
No.
No. Exactly.
So it's, yeah, there is, you can represent R3 with any combination of A1, A2,
Exactly.
A3.
There is no issue with consistency in here. So no matter what B1, B3, B2, I can solve for that. So this system is consistent for all values, no matter what B1 and B2. Because, why because? Because the consistency comes from this scenario, 0, 0, 0, non-zero. That's where the consistency comes from. And I don't have a row of this form because there is no row of the form, this format. Okay? So no matter what you give me here, no matter what you give me, I'm gonna get you those x1, x2, x3, no matter what this. And 0 is the one that bothers student, but it shouldn't, because if this is 0, as I said, it means your x3 is 0. All right, why not? It's a number. All right, so the span is equal to R3 because as you guys said, any vector, I can represent it as a combination. You throw any vector at me. You wanna throw pi e square root of 2? Yes, pi e square root of 2, I can write it as a combination of those 3 vectors. Those 3 vectors are gonna fill out the 3 space. They're gonna be like this, basically. That's the picture. This, this, and that. So anything, I will be able to write it as their combination. All right. You guys can keep asking questions. Anybody?
Hello.
I'm with you.
May I see the bottom of that paper, please?
Okay. Any other questions?
I'll just jot this down.
Deniki, any question?
How long do we have after class is over to submit the test?
Like the quizzes, what do I give you on the quiz? I give you half an hour after the class time.
Okay, good.
Okay, that should be plenty of time.
Mhm.
The regular class, usually it was an hour, 15 minutes. And now I'm giving you like 40 extra minutes. And I imagine that should do for technology. All right, good enough? Okay, any other questions? Just ask anything. It's your day. Okay, so good luck. And if you have a question at the last
I'm
minute,
sorry.
what?
I'm terribly sorry. I had a question about this one possible scenario.
Yes.
I forgot to mention this during class. Problem 13 from section 1.4. There was the scenario where you were expected to multiply matrix A times the vector
Wait,
0, 4, 4.
wait, I didn't memorize the number. So it's number what?
13 from section 1.4 of the book.
Okay,
I forgot to mention this during class. I'm sorry.
that's all right.
So what happened is that it was one of those AX equals B problems. And B in this case, or rather U as they had it there, was vector 0, 4, 4.
Yes.
And the only way, for it to be, the only way for the problem to even work was to disregard the 0 and just treat it as vector.
No, you cannot disregard anything.
Okay.
You cannot disregard anything. You set up, whenever you have a question, you ask yourself, what are they asking me? And you solve it. You don't disregard.
Oh yeah, sorry.
Okay,
I didn't word. I'm sorry, no, I didn't word that right. It was actually B, and the thing is that.
Are you talking about the problem I'm showing it on Zoom?
Yes.
Okay, so the
Yes.
question is U. So these are the columns of A. These are the columns. And the question is U in the plane spanned by the column of A. So the column of A are this vector and this vector.
Yes.
And when I take their span, I get a plane. And the question is U in this plane, which is really basically asking you, is U a linear combination, yes or not? That's really what the question is about. Shall I repeat?
Yes. Yes. I mean, I got it. I understand. It did turn out to.
All right. So now, the way you do it, there is one way. One way. You have to set up the following. You have to look for weights, x1 and x2. You ask yourself, can I find weight? x1, such that this is my first vector, and this is my second vector. And the question is, can I find weight x1, x2, so that 0, 4, 4 is a combination of those vectors? Never disregard. So we set up the augmented matrix, and we solve. With me?
Yes.
You don't disregard, you solve. And if you find a solution, it means it is in the span of those two vectors because it's the linear combination. If you don't find a solution, it means it's not in the span. It means it's not in the plane. You cannot reach it following the two directions. You have two vectors. It's not in the span. It means you cannot start from here and reach your vector by following the direction of those two. No way. This vector is outside. It's right there.
Okay.
That's where your vector is.
Right.
All right? Now you know how to solve that, and then it depends on your answer.
Yeah. My real question, I think, was, does the 0 make a difference?
Okay. You know what? Let's do it together. So suppose you have this, and we're going to reduce it. All right? Solve for it. 3 minus 2, 1, minus 5, 6, 1, 0, 4, 4. All right? How would you solve it?
You would row reduce to echelon form.
Yeah, what would be your first step?
First step would be to switch the rows R1 and R3, so that there's a 1 there. Simplify things. Then from there you would multiply. You would multiply row 1 by 2 and add it to R2 to get a new R2. That
Right.
would get you
So
0.
the 0 is not an issue. I mean, the 0 is just being switched. So I will get a 0 and get here an 8, right? 2 times 4, 8 plus 4, that's a 12.
Yeah.
This is 0, minus 3 plus 3. Now minus 3 minus 8, minus 12. Correct?
Yes.
All right, and now I'm not in echelon form. Not in echelon form. You don't stop. But it's clear what's happening. 8 minus 8 is 0. 12 minus 12, it's a 0.
All right.
So is there a solution?
Okay. Yeah, I
Is
got
the
it.
system consistent?
Yes, it is.
Absolutely. Because we can solve. There is no inconsistency. There is no 0, 0, non-zero. So x2 will be 12 over 8, which is we divide by 4, 3/2. And x1 is 4 minus x2. It means 4 minus 3/2, which is 5/2. All right? It means the vector u can be written as 5/2 times the first column of A plus 3/2 the second column of A. So it is absolutely in the span because it's a linear combination.
Okay, I got it. Thank you.
Any other questions?
Before I go, one other question, please. Actually, it's kind of two questions. One, let me get this straight. So the exam starts at 2 o'clock, goes to 3:15. Then
I will open it at 1:50.
1:50.
Yeah.
Okay. And goes to 3:15. Then after that, we have to 3:45.
You take like half an hour to do whatever you do, you know, scan and pick it into a PDF document. So I will close it at, let us see, at 3:45.
Close the meeting.
What?
Close the meeting.
Yes, yeah.
Okay.
Everything and the exam.
Right. And the other question was, let me see if I got this straight. For the true/false questions,
Yes.
For our true or false answer, we're going to have to provide a justification.
It depends on my question.
Okay.
Right? If my question is provide an explanation, which is I may do, then you will have to. If I said true or false, no justification is required, then you're lucky.
Okay. All right. I got it. Thank you.
Okay, anything else? Okay, anybody else? Okay, shall I end the meeting? Okay, actually I have office hours now. If you guys still have questions, you can meet me in my office hours. All right?
Okay.
Bye.